So this is the Unit 2 study guide for our Unit 2 exam over force and motion. So the very first question on here says, what is the formula for momentum? This is definitely a formula you want to know, and the triangle you probably ought to know. So the formula, remember, is P, which is momentum, is equal to mass times velocity or speed. And the triangle that we use there, whereas we had momentum up here, we had mass in the bottom left, and then we had velocity or speed in the bottom right. Either one is fine. Okay, for the second question, what does a conservation of momentum mean? It just means that in a collision, whatever momentum there was before the collision has to be the same as the momentum after the collision. So that's the conservation of the momentum. Number 3 says, what is the formula for conservation of momentum? And we've seen this a couple different ways. One of them is the momentum of object 1 plus the momentum of object 2 equals the momentum of object 1 plus the momentum of object 2. The difference in these sides is the left side, remember, was before the collision, and the right side was after the collision. The other way that we've seen this formula is m1v1, which is the momentum of object 1, plus m2v2, which is the momentum of object 2, equaling m1v1 prime plus m2v2 prime. And these primes just indicate after the collision. So again, all of this stuff on the right-hand side is after the collision. And again, this prime symbol here that's with the velocities is just meaning after the collision. The masses, there's no prime because the mass is the same either way. And then the left-hand side, again, was before the collision. All right, in our next question there under forces, it says, how is force defined? Remember that the definition of force is a push or a pull. The net force is just the sum of all the forces that are acting on an object. And then we use this term balanced forces or balance forces just to say that the overall net force is 0. And in other words, there is no motion in the object. So the object is not moving. The object is stationary or still if the net force is 0 or we have balanced forces. As far as unbalanced forces go, that just means that there is motion in the object. So the object is moving in some direction or with some speed. So it can be either or both things may be happening. And in an unbalanced force, the net force has an actual value to it. It is not 0. Okay, now for the units of force with its abbreviation. Remember that the units can be written as kilogram times meter per second squared, which is also known as a Newton, which is a capital N. In our next question here, it says Bill, Jane, Peter are pulling a rope with a force of 125 newtons, 100 newtons, and 200 newtons, respectively. And this word respectively just means that they're in the same order as the names that were given. So Bill is pulling at 125 newtons, Jane at 100 newtons, and Peter at 200 newtons. And then Fred, John, and Lisa are pulling the opposite direction with a 150 newton, 130 newton, and 150 newton force. And again, that's respectively, which means that the first person is pulling with the first force, the second person is pulling with the second force, and the third person, Lisa, is pulling with 150 newtons, or the third force. And it says, what is the net force on the rope? Okay, so we can say in this direction we have Bill, Jane, and Peter pulling, and we know that the net force in that direction, one, it's negative because they're pulling to the left, and remember we define the left as being negative and the right as being positive. So we have negative 125 newtons plus a negative 100 newtons plus a negative 200 newtons. What that means is that these three are pulling with an overall force of 425 newtons in the direction to the left, which is that negative sign. And then as far as the other three, they're pulling in that direction with a positive 150 newtons and a positive 130 newtons and a positive 150 newtons. So the overall pull in this direction, or the positive direction then, is going to be 430 newtons by Fred, John, and Lisa. Fred, John, and Lisa. Okay, our next question here, number 12, is asking us about the three basic types of friction. And I know this is confusing because in class we actually went over 4 types of friction, but you're only responsible for the first 3 types of friction, which I'll go over here. The ones that you're responsible for are static friction, which is just the friction between objects that are at rest. And remember that in order to start an object moving, that's the one that we have to overcome. The second one that you're responsible for is sliding friction, and that's when 2 objects are sliding across each other. And the third one that you're actually responsible for is rolling friction, which is the friction caused by wheels on a surface. The fourth one that we did go over in class that you are not responsible for is fluid friction. So don't worry about fluid friction. Fluid friction was the type of friction we talked about if you're swimming in a pool or a plane was going through the air. That air resistance would technically be called fluid friction. Okay, our next question on here says, how would you recognize if unbalanced forces are acting on an object? And here we know that they're going to be unbalanced forces if that object is moving. That's the only time we're going to have a moving object, is if there are unbalanced forces in play. And then 14, how would you recognize if balanced forces are acting on an object? Here the net force is going to be 0, whereas in unbalanced forces we're going to have a net force. And the thing that we would observe with balanced forces is there would be no motion or no movement. So when the net force is 0, we have no motion. Okay, so the common forces that we see on free body diagrams are the applied force, which we usually label as F sub APP, the gravity force, which is F sub grav, the normal force, which is F sub norm. Remember, there's also a frictional force, which we usually define as F sub fric. Air resistance, which is F sub air. And then tension force, which is F sub TENS. And again, definition-wise, the applied force is just a force that's being applied by a person or another object, like if you're pushing a box across the floor. And then the gravity force, or F sub grav, is the force of gravity on an object. And it can be on any major body like the Earth, the Moon, or some other kind of planet. Then the normal force is a supportive force that's exerted on an object that's in contact with another stable object, Like if a book is resting on a table, the table itself is applying a normal force to the book. Frictional force is always that force that's caused by friction that's in the opposite direction of an applied force. And then air resistance is just as it sounds, or the air force, or the air resistance force is just a special type of frictional force that's caused by an object traveling through the air. And the last one here, that tensional force, is a force that's caused by the tension of a string, a rope, or cable, a wire, something like that. So this next question here, number 16, says the 6 students in the tug-of-war contest on 11. So we're trying to come up with a free body diagram for that. So we can call this our rope. And if that's our rope, we had 3 applied forces on either side. So Bill had the least force, which means she should have the smallest arrow. I'm sorry, actually, Jane had the smallest force, so she should have the smallest arrow. And then there was a little bit bigger arrow, and then an even bigger arrow for Peter, who had 200 Newton force. So these were all applied forces. So I could label them as all F sub APP. And then we had 3 forces in the opposite direction, 150, 130, and 150. So we had 2 forces that were the exact same size, and then we had 1 force that was a little bit less at 130 newtons. And again, these are also all applied forces. Alright, for the refrigerator being pushed up a ramp, here is our ramp, let's say, and there is our refrigerator. We know that we have the force of gravity going down. We also have a normal force that's going to be perpendicular to the ramp. And if we're actually pushing the refrigerator up, then we're going to have an applied force going up the ramp. And we're going to have a small frictional force going in the opposite direction of our applied force. So that's kind of what our force diagram would look like for that. Okay, our next force diagram is going to be a skydiver falling through the air, and that's before his parachute opens. So here we have our skydiver, we have the force of gravity pulling on him, and we also have the force of air resistance, which we're going to label that way. So that's what that looks like. And we need to make sure that that arrow for the air resistance is smaller than the arrow for gravity. And then the last one here says a skydiver descends and his parachute actually opens. So now that his parachute is open, we have a very big arrow for our air resistance force, which hopefully is smaller than the gravity force that's pulling him down, which would help to stop him from crashing into the ground. Alright, our next question on the review sheet says, to what kind of objects does Newton's law of gravitation apply? And here we need to understand that Newton's law of gravitation applies to every single object in the universe. So all the objects in the universe. And the next question here says, what is weight? So weight has a formula, and weight is essentially just the force of gravity, or the acceleration of gravity, and the force of the mass, or the force of matter on a planet. So the equation that we're looking at there is weight is equal to mass times the acceleration of gravity, which remember on Earth is 9.8 meters per second squared. So that is also the answer to this question. And remember that mass for this question here is just how much stuff or how much matter is in an object, whereas weight is that mass with an applied force, and that force is gravity. So that's how weight is different. Weight is accounting for the acceleration of gravity. The next question on here says, what is the value for Earth's gravitational strength? Which I went over just a second ago. That's 9.8 meters per second squared. Remember, all accelerations have this unit of meters per second squared, or some distance over some time squared. And so 9.8 meters per second squared. All right, for Newton's laws, our first law is that law of inertia, which means that an object at rest will stay at rest unless acted upon by another object, and an object that is at rest will stay at rest until it's acted upon by another object. So again, this idea of inertia is Newton's first law. So our next question here says, according to Newton, if forces on an object are balanced, what does that say about the motion of the object? And basically that means that if it's at rest, it's going to stay at rest. So it's going to remain the same if the forces are balanced. So there's not going to be any motion if the forces are balanced. And then this idea of inertia, or Newton's first law, just means that that's the tendency of an object to resist change. As far as how mass affects inertia, the higher the mass, the more the inertia is going to be. So we had that example of a bowling ball rolling versus a beach ball rolling. And all objects are going to resist change based on Newton's first law. All right, for this question here, briefly explain how inertia works or is illustrated by passengers in a car. Here, if a car is traveling down a road at 50 miles an hour, that also means that the people that are in the car are moving at that exact same speed. So they're moving at 50 miles an hour also. Now, if the car stops, the people are going to continue to move at that speed of 50 miles an hour. So that was like that physics of car crashes video that we watched. Okay, and our next question says, what is Newton's second law? Newton's second law says that unbalanced forces acting on an object is going to be equal to the object's mass times its acceleration. So it's this idea of force. So force equaling the mass times the acceleration. Newton's second law deals with unbalanced forces, pretty much. And then the formula used to describe his law I've written up here. Force equals mass times acceleration. And then according to Newton's second law, if I apply a force on an object, what should it do? If you're applying a force on an object, then the acceleration is going to increase since the mass isn't changing at all. So the force is going to increase on that object as well since the acceleration is increasing. Newton's third law says that for every action there is an equal and opposite reaction. And then this asks us to list 4 facts from Newton's third law, which I'll write up here. The first one is that forces are always acting in pairs. So if there's an action force, there's a reaction force. And then the second one is that forces are the same size but in opposite directions. The third one is that forces do not act on the same object. And then the fourth and last one are forces occur at the same exact time in Newton's third law. Okay, our next question here says, what is the weight in newtons of 75 kilogram person? So here we need to remember that our equation for weight is that weight is equal to mass times the acceleration of gravity. So that means we're going to take the 75 kilogram person and multiply it by the acceleration of gravity, which you need to memorize as 9.8 meters per second squared. So then our answer then, if you put that in your calculator, is 735 kilogram times meter per second squared, which remember is newtons. So the answer for this one should be 735 newtons for the weight. So in number 39, we have a different gravitational force because we're on the moon instead of the Earth. So the equation is the same, so weight equals mass times g, but this time gravity is going to be changed. So the mass is still 75, but this time our acceleration is only 1.6 meters per second squared. So that same person then is going to weigh 120 newtons, or 120 kilograms per meter times meter per second squared. And the last question on here says if a 150 kilogram person could stand on the surface of Jupiter, the person would weigh 381 newtons. What is the gravitational strength? So again, using the same equation where weight equals mass times gravity, this time we're actually going to be looking for gravity. So we know that the weight is 381 newtons. So if we wanted to make a triangle for this, we could say weight in the top, mass in the bottom left, and gravity in the bottom right. And if we're looking for gravity, that's going to be weight over the mass. So 381 divided by the mass of 150, which is going to be 2.54, and we know the unit for gravity or acceleration again is meters per second squared. So our answer there should be 2.54 meters per second squared. So question 41 on here says, what is the net force necessary for a 2,000 kilogram automobile to accelerate forward at 5.0 meters per second squared? Well, here we know that force is equal to mass times acceleration. So we're looking for the force. We know the mass is 2,000 kilograms, and we know the acceleration is 5.0. And remember, whenever we're multiplying mass in kilograms by acceleration meters per second squared, that unit is going to be newtons. So 2,000 times 5, our answer there is going to be 10,000 newtons. And 42 says, what is the acceleration of a 15 kilogram object given a force of 500 newtons? So using that same equation, this time we have the force and we have the mass, but we are looking for the acceleration. So to solve for this, we're going to take 500 divided by 1500, which is 0.33. And remember, our units for acceleration are meters per second squared. And in the next question it says, in a test garage, a 2,500 kilogram car goes from rest to 20 meters per second in 5 seconds. So this information here is trying to give us the acceleration. Remember, the acceleration is the velocity divided by the time, which is 20 divided by 5. So that's 4 meters per second squared. So that's the acceleration. It says how much force is this car going to have if it crashed. So that's going to be 2,500 kilograms, which is the mass, times this acceleration that we determined as 4. So that's going to be 10,000 newtons for the force. Okay, now for 44, it says a runner covers a distance of 50 meters in 4 seconds, and the runner has a mass of 55 kilograms. What is its momentum? What is the runner's momentum? Remember that momentum is mass times velocity. So that's going to be 55 kilograms times its velocity, which it didn't give us, straightforward, but the velocity is distance over time, so that's 50 over the 4 seconds. Which means this guy's momentum, or the runner's momentum, is 687.5. And remember, the units for momentum are kilogram time meter per second. So 687.5 kilogram meter per second. 45 says a toy truck has a momentum of 150. So we know P is 150, and it has a speed of 3.5 meters per second. What is the mass? So this time we're looking for the mass, and we're given the velocity of 3.5. So to find the mass, we can take 150 divided by the 3.5, which is 42.86-ish. So the mass of this truck is 42.86 kilograms. So number 46 says that a cue ball with a momentum of 2 kilogram times meter per second is hit into a stationary 8 ball. After the hit, the cue ball has a momentum of 1.25 kilograms per meter times meters per second. What is the momentum of the 8 ball after the collision? So this is a conservation of momentum problem. And remember, with conservation of momentum, m1 times v1 plus m2 times v2 all before the collision is equal to m1 times v1 prime, which means after the collision, plus m2 times v2 prime, which again, the primes just mean after the collision. So this thing right here is the momentum of object 1 before the collision, the object of momentum 2 before the collision. Here is our momentum of object 1 after the collision. Here is our momentum of object 2 after the collision. And so with the momentum of the cue ball, if we want to call the cue ball object 1, and the 8 ball object 2, the momentum before the collision is 2, so we have 2 plus 0. Since the 8 ball is not moving, oops, sorry about that bell. Since the 8 ball is not moving, it has no momentum because its velocity is 0. So 2 plus 0 is going to equal the 1.25, which it tells us is the momentum after the collision, plus P2, which it's asking us is what is the momentum of that 8 ball. So then doing our algebra here, we can figure out that P2 is going to equal 2 minus 1.25. So that's going to be 0.75. And our units for the momentum, remember, are kilogram times meter over second. Okay, this last question says a cue ball with a mass of 3 kilograms and a velocity of 5 meters per second is crashed into a stationary baseball with a mass of 4 kilograms. After the crash, the cue ball is traveling at a velocity of 3 meters per second. What is the velocity of the baseball? So we know we have two objects here. We have a cue ball and a baseball. And let's set up our data here so that we can have this information before the crash and after the crash. before the crash, we know the mass of the cue ball is 3, and we know its velocity before this crash is 5 meters per second. We know the mass of the baseball is 4 kilograms before the crash. And it's stationary, so its velocity before the crash is 0. So again, all of this stuff is before the crash. And now let's write out the information for after the crash. After the crash, the mass of the cue ball is the same. It's still 3, just like the mass of the baseball is still 4. And I'm just realizing now I messed up the subscript here. These should be 2 instead of 1, because 1 is the cue ball, and we're making 2 the baseball. And the velocity of the cue ball after the crash is 3. So the velocity is 3 meters per second, and we're trying to find the velocity of the baseball after the crash. So here we're going to be using this m1 v1 plus m2 v2 equaling m1 v1 prime plus m2 v1 prime. These are both prime because they're after the crash. So our equation then is going to be 3 times 5, which is 15. This is 0. This is 9. So 15 plus 0, that's all before the crash, has to equal the momentum after the crash. So that's going to be 9 plus 4 times v2 prime. And then we'll be solving for v2 prime, which is after the crash. So that means that 6 is equal to 4 times v2 prime, which means that v2 prime, or the velocity of the baseball after the crash, is 6 divided by 4, which is 1.5. And we know the units for velocity are typically meters per second, so we need to put the units there of meters per second. So the answer there for that very last problem, number 47, is 1.5 meters per second.